Imagine stepping outside on a crisp night in 1781, carrying a telescope you built with your own hands. You're not searching for anything in particular, just methodically cataloguing the stars the way a gardener might tend each flower bed in turn. Then, in the eyepiece, you notice something that doesn't belong, a tiny disk of pale light where your star charts show only empty space. At first, you think it might be a comet, perhaps a distant nebula. But night after night, it moves against the backdrop of stars in a way that whispers of something far more extraordinary. You've just doubled the size of the known solar system. Hello and welcome to the Sleepy Astronomer. Tonight, we're drifting outward to one of the most peculiar worlds in our cosmic neighborhood. A planet that rolls through space on its side like a cosmic bowling ball, wrapped in an atmosphere so featureless it seems almost shy. A world where seasons last longer than human lifetimes, where rings circle in impossible orientations, and where moons bear the names of Shakespearean characters dancing through an alien sky. If you're settling in for the first time, welcome aboard our gentle journey through the cosmos. And if you've travelled with me before to explore the quiet wonders of space, it's wonderful to have you back among the stars. Whether you're tucked into bed, curled up on a favourite chair, or perhaps lying back where you can see the night sky through a window, I'm so glad you're here. Our journey begins with one of astronomy's most serendipitous discoveries, when a musician turned stargazer accidentally stumbled upon a world that shattered humanity's ancient assumptions about the boundaries of our solar system. For thousands of years, Saturn had marked the edge of the known cosmos, the last wandering light visible to naked eyes. Beyond lay only the eternal, unchanging realm of fixed stars. William Herschel's homemade telescope changed all that on a single March night, revealing that the universe was far larger and stranger than anyone had dared imagine. What he discovered wasn't just another world circling our sun, but a planet so fundamentally different from everything we thought we knew that it would challenge the very foundations of planetary science. Picture a world that has somehow been knocked completely sideways, rolling through its orbit like a barrel tumbling down an endless hill. This is Uranus, a planet tilted at such an impossible angle that its seasons last decades, where north and south poles take turns basking in sunlight across years that stretch longer than human lifetimes. Its magnetic field points in directions that shouldn't exist. Its moons circle in orientations that seem to mock our sense of cosmic order, while rings of dark material trace circles through space in ways that challenge our understanding of how planets form and behave. There's something beautifully humbling about Uranus, a world that reminds us that the universe doesn't arrange itself for our convenience. It exists according to its own mysterious logic, shaped by cosmic accidents and ancient violence we're only beginning to understand. In its sideways spin and featureless face, we find echoes of processes so vast and patient they unfold across billions of years. Tonight, we'll follow the trail from Herschel's Garden Observatory to Voyager's lonely encounter at the edge of the solar system. We'll explore a world where the very concepts of up and down lose their meaning, where north and south poles take turns facing the sun across decades-long seasons, and where the familiar rules of planetary behavior simply don't apply. From the romance of its accidental discovery to the ongoing mysteries that still puzzle astronomers today, Uranus stands as a reminder that even in our own solar system, there are worlds strange enough to stretch the imagination. It's a planet that teaches patience, both in the slow rhythms of its distant orbit and in our gradual understanding of its secrets. So settle in, get comfortable, take a slow, deep breath, and let's begin our gentle drift outward. Past the familiar territories of Mars and Jupiter, beyond Saturn's majestic rings, to where a pale blue-green wanderer rolls through the darkness on its side. Out there, 19 times farther from the sun than we are, Uranus waits, patient, tilted, and beautifully mysterious, ready to share the story of how one musician's curiosity revealed that our cosmic home is larger and more wonderful than we ever dared to dream. Picture a tall, lean man standing in the garden behind his house on New King Street in Bath, England, sometime around midnight on a crisp March evening in 1781. The air carries that particular stillness that comes with late nights in early spring, when the world feels poised between winter's grip and the promise of warmer days ahead. William Herschel adjusts the focus on his handcrafted telescope, a 7-foot reflecting instrument that he ground and polished himself with the patience of someone who understands that perfection comes only through countless hours of careful work. At 42, Herschel is known throughout Bath not as an astronomer, but as a musician. By day, he serves as the organist at the Octagon Chapel, his fingers dancing across keys in the service of hymns and sacred music. In the evenings, when his musical duties are complete, he transforms his small garden into an observatory, methodically sweeping the night sky with a kind of systematic precision that mirrors the mathematical foundations of the music he loves. There's something deeply poetic about this dual life, days filled with the harmonious mathematics of musical composition, nights spent listening to the silent symphony of the stars. Herschel understands, perhaps better than most, that the universe operates according to patterns and relationships that can be as beautiful as any melody, as structured as any fugue. In both music and astronomy, he seeks the underlying order that governs seemingly chaotic complexity. On this particular evening, March 13th, 1781, Herschel is engaged in what he calls his Review of the Heavens, a systematic survey designed to catalogue every celestial object visible through his increasingly powerful telescopes. It's methodical work, requiring the kind of patient attention to detail that characterizes both accomplished musicians and dedicated astronomers. He moves his telescope in careful sweeps across the sky, noting the position and characteristics of each point of light that passes through his field of view. In the constellation Gemini, something catches his attention. Among the familiar pinpricks of starlight, there's a disk, small, pale, but definitely showing a measurable width rather than the sharp point of light that characterizes even the brightest stars. At first, his musical mind jumps to the most likely explanation. A comet, perhaps one of those mysterious visitors from the outer reaches of the solar system that occasionally grace our skies with their ghostly presence. But as the nights pass, and Herschel returns again and again to observe this curious object, it begins to reveal characteristics that don't quite fit the comet hypothesis. Comets, in his experience, show the fuzzy, irregular appearance of cosmic snowballs beginning to sublimate as they approach the sun's warmth. This object, by contrast, maintains a steady, disk-like appearance. More puzzling still, it seems to move against the background stars with a regularity that suggests something far more profound than a chance visitor to our solar neighbourhood. Night after night, Herschel tracks the mysterious object's motion. His musician's ear for patterns helps him recognize that this isn't the erratic path of a comet falling toward the sun, but something altogether more systematic. The object is following what appears to be a regular orbit, not the elongated ellipse typical of comets, but something approaching a circle. This realization sends a thrill through his methodical astronomer's mind. Could this be something unprecedented in the history of human observation? Word of Herschel's discovery spreads through the tight-knit community of 18th century astronomers with the kind of electric excitement that accompanies genuinely revolutionary discoveries. Letters cross between observatories across Europe as astronomers turn their own instruments toward the coordinates Herschel has provided. The mathematician Anders Johann Lexell, working in St. Petersburg, begins the painstaking process of calculating orbital elements based on the accumulating positional observations. What emerges from these calculations is nothing short of extraordinary. The mysterious object isn't following the highly elliptical path typical of comets, but rather traces a nearly circular orbit around the Sun at a distance roughly twice that of Saturn. This is no visitor from the outer darkness. It's a permanent resident of our solar system, a world that has been quietly circling our star for billions of years, unnoticed by human eyes, until Herschel's careful observations brought it into the light of scientific recognition. The implications ripple through the astronomical community like harmonics resonating from a struck bell. For thousands of years, since the dawn of human consciousness, the solar system had consisted of 6 wandering lights: Mercury, Venus, Mars, Jupiter and Saturn, plus Earth itself. These were the classical planets, known to ancient astronomers from Babylon to China, from Greece to the Americas. Beyond Saturn lay only the realm of fixed stars, distant suns that maintained their eternal patterns across the celestial sphere. Herschel's discovery shatters this ancient boundary. In a single observation, humanity's cosmic neighbourhood has doubled in size. Where once Saturn marked the frontier of the known solar system, now there's another world twice as distant, rolling through the darkness in the cold outer reaches where sunlight arrives as little more than a distant gleam. The social world of 18th century astronomy plays out in fascinating ways around Herschel's discovery. This is an era when serious astronomical work often depends on royal patronage and aristocratic curiosity. King George III, himself interested in the sciences, becomes Herschel's patron, providing the financial support that allows the musician astronomer to dedicate more time to his celestial observations. In return, Herschel proposes to name his discovery Georgium Sidus, George's star, a gesture of gratitude that reflects the political realities of scientific work in the age of absolute monarchy. But the international community of astronomers has other ideas. Johann Bode, the German astronomer whose star catalogues and maps have become standard references, suggests instead the name Uranus, after the Greek primordial deity of the sky, father of Saturn in classical mythology. This choice maintains the tradition of naming planets after ancient gods, while extending the family tree backward in time. Where Saturn represented the father of the gods in Roman mythology, Uranus represents the grandfather, the even more ancient sky god, whose realm encompasses all of heaven. The mythological resonance feels appropriate in ways that perhaps even Bode didn't fully anticipate. In Greek cosmology, Uranus was the primordial sky god, the first ruler of the universe who was eventually overthrown by his son Saturn in a cosmic revolution that established a new order among the gods. There's something fitting about placing this ancient deity at the frontier of the known solar system, representing the boundary between the familiar realm of classical planets and the unknown territories that stretch toward the stars. The discovery also carries profound theological implications in an era when the structure of the cosmos is still intimately connected to religious understanding. The traditional view, inherited from medieval Christianity, pictures a finite universe with Earth at its center and the sphere of fixed stars marking its outermost boundary. Herschel's planet pushes that boundary outward, suggesting that the universe might be far larger than comfortable theological frameworks allow. There's a beautiful irony in the fact that this cosmic revolution begins in the garden of a church organist. The same mathematical principles that allow Herschel to understand musical harmony also enable him to recognize the regular patterns that distinguish planetary motion from the random appearances of comets. In both domains, musical and astronomical, he's listening for the underlying order that gives meaning to apparent chaos. The technical achievement of Herschel's discovery reflects not just keen observation, but also remarkable craftsmanship. The telescopes of his era are entirely handmade, requiring their creators to grind and polish mirrors with extraordinary precision. Herschel's 7-foot reflector, the instrument through which he first spotted his planet, represents hundreds of hours of careful work, a labour of love that combines the precision of scientific instrumentation with the artistry of a master craftsman. But perhaps the most remarkable aspect of the discovery is its accidental nature. Herschel isn't searching for a new planet when he stumbles upon his pale disk in Gemini. He's simply engaged in the systematic work of mapping the heavens, cataloguing what's already there rather than seeking something unprecedented. This speaks to a fundamental truth about scientific discovery, that the most revolutionary findings often come not from seeking specific answers, but from maintaining the kind of open, methodical attention that allows unexpected patterns to reveal themselves. As news of the discovery spreads through European intellectual circles, it captures the public imagination in ways that purely technical astronomical work rarely achieves. Here is something that speaks to the fundamental human sense of exploration and discovery. The solar system, humanity's cosmic home, has suddenly become larger and more mysterious. Beyond the familiar wandering lights that have guided navigation and shaped calendars since the dawn of civilization lies another world, rolling through the darkness at distances that stretch the imagination. The discovery also marks a transition in the nature of astronomical work itself. Previous planetary discoveries belong to prehistory. Mercury, Venus, Mars, Jupiter, and Saturn have been known since humans first looked up at the night sky and noticed that some stars wander while others remain fixed. Herschel's planet is the first world discovered through the systematic application of improved technology and careful observation. It represents the birth of modern planetary astronomy, the beginning of humanity's systematic exploration of the solar system through scientific method rather than naked-eye observation. In the years following the discovery, as more powerful telescopes reveal additional details about the new world, it becomes clear that Herschel has opened a door to realms stranger than anyone imagined. His planet will prove to be tilted on its side in ways that challenge basic assumptions about planetary formation. It will reveal a system of rings and moons that circle in orientations that seem to mock conventional understanding of cosmic order. Most mysteriously, it will appear almost featureless through even the best telescopes, presenting a bland, uniform face that hides its secrets behind atmospheric veils. But all of that lies in the future. On this March night in 1781 in a garden in Bath, a musician with calloused fingers from grinding telescope mirrors peers through his handcrafted instrument and notices something that doesn't quite belong among the familiar patterns of stars. In that moment of recognition, the instant when careful observation reveals that the universe is larger and stranger than we thought, William Herschel steps across the threshold into a new era of cosmic understanding. As we prepare to follow Herschel's accidental planet on its journey through the outer solar system, we carry with us the spirit of that moment, the recognition that the most profound discoveries often come not from seeking specific answers, but from maintaining the patient, systematic attention that allows the universe to reveal its secrets in its own time. Like a musician listening for the subtle harmonies that underlie complex compositions, Herschel teaches us that the cosmos rewards those who combine technical skill with patient observation, who remain open to the possibility that the night sky still holds surprises waiting to be discovered by anyone willing to look closely enough. And what Herschel discovered that night would prove to be far stranger than anyone could have anticipated, a world that rolls through space in ways that challenge our very understanding of how planets should behave. Beginning with the most fundamental question of all: which way is up when you're spinning on your side? Imagine trying to explain to someone what it means for a world to be tilted on its side. You might start by describing how Earth spins like a top, its axis pointing roughly toward the North Star, creating the familiar rhythm of day and night as our planet turns beneath the sun's steady gaze. Then you'd have to ask them to picture that same world knock completely over, not just leaning at a gentle angle like a spinning top beginning to wobble, but rolled onto its side so thoroughly that what used to be its north pole now points almost directly at the sun. This is the reality of Uranus, a world tilted at an impossible 98 degrees from what we might consider upright. If Earth's modest 23-degree tilt gives us our familiar seasons, imagine what happens when a planet's axis lies almost flat in the plane of its orbit. Picture a world where the concept of up and down becomes meaningless, where seasons last not months but decades, and where the sun rises and sets in ways that would leave any earthly observer completely disoriented. The numbers themselves tell only part of the story. 98 degrees of tilt means that Uranus isn't just lying on its side, it's actually rotating slightly backward as well, rolling through its orbit like a barrel that's been knocked end over end and never quite recovered its original orientation. To stand on Uranus, if such a thing were possible, would be to experience a world where the fundamental assumptions about planetary behaviour simply don't apply. During Uranus's summer, one hemisphere basks in continuous sunlight for 21 Earth years, while the opposite hemisphere endures an equally long winter of perpetual darkness. Imagine a season that lasts longer than most human careers, where children born at the beginning of summer might not experience their first winter until they're well into adulthood. The concept stretches our earthly understanding of seasonal change beyond all recognition. How does a world end up in such an extraordinary state? The most widely accepted explanation reads like a tale of cosmic violence written across billions of years. Picture the young solar system, still chaotic with debris and forming planets, where collisions between massive objects were not rare accidents but regular features of planetary evolution. In this crowded cosmic construction zone, Uranus likely suffered a catastrophic impact, perhaps with another planet-sized body or possibly with multiple smaller objects over time. The collision that knocked Uranus sideways would have been an event of almost unimaginable violence. Picture two worlds, each roughly the size of Earth or larger, converging on intersecting orbits at velocities measured in kilometers per second. The impact would have released energy equivalent to trillions of nuclear weapons, vaporizing portions of both worlds and sending shockwaves through the structure of the forming planet that would reshape its interior and permanently alter its spin. Yet there's also beauty in considering alternative theories. Some planetary scientists suggest that Uranus's extreme tilt might have developed gradually through a complex gravitational dance with its neighbours during the solar system's youth. In this gentler scenario, gravitational resonances, those invisible rhythms that govern planetary orbits, could have slowly nudged Uranus's rotational axis further and further from vertical over millions of years, like a cosmic version of a spinning top, gradually slowing down and falling over. The truth might lie somewhere between catastrophic impact and gradual evolution. Perhaps Uranus suffered multiple smaller collisions over time, each one nudging its axis a bit further from vertical until the cumulative effect left it rolling on its side through the outer darkness. The mystery reminds us that even in our own solar system, the stories written in planetary characteristics often reach back to events so ancient and violent that we can only guess at their true nature. The effects of Uranus's sideways orientation extend far beyond the obvious strangeness of decades-long seasons. Consider the planet's magnetic field, that invisible shield that most worlds generate through the rotation of molten material in their cores. On Earth, our magnetic field roughly aligns with our rotational axis. Compass needles point toward magnetic north, which lies reasonably close to the geographic North Pole. Uranus's magnetic field, by contrast, is tilted nearly 60 degrees from its rotational axis and doesn't even pass through the planet's center. Picture trying to navigate with a compass on such a world. Magnetic north would point in a direction that bears no relationship to the planet's spin, creating a navigational nightmare that reflects the deeper mystery of how Uranus generates its magnetism in the first place. The offset, tilted magnetic field suggests that the planet's interior structure might be as disrupted as its external orientation, perhaps a legacy of whatever ancient violence knocked it sideways in the first place. The ring system that circles Uranus provides another window into the planet's sideways nature. Unlike Saturn's rings, which lie in the plane of that planet's equator and appear edge-on when Saturn's axis points toward us, Uranus's rings circle the planet's tilted equator like the rim of a wagon wheel rolling down a cosmic hill. When Voyager 2 encountered Uranus in 1986, these rings appeared almost face-on to the spacecraft, creating images that look like dark, narrow bands crossing the planet's face, a perspective that would be impossible for any normally oriented world. There's something almost melancholic about contemplating Uranus's seasons. On Earth, the changing seasons create cycles of renewal and dormancy that have shaped life's evolution and human culture in countless ways. The gradual shortening of days as winter approaches, the return of warmth with spring's arrival. These rhythms operate on timescales that match human experience and biological cycles. On Uranus, seasons unfold with geological patience. A single winter lasts longer than the entire span of recorded human history. Imagine being born during the long polar night and living your entire life waiting for the sun to rise, not tomorrow or next season, but decades in the future. The timescales involved stretch human imagination beyond its comfortable limits, forcing us to contemplate planetary processes that unfold with patience that dwarfs any earthly cycle. Consider what it might mean to experience such seasons if you could somehow survive on Uranus's surface. During the planet's approach to summer solstice, you might spend years watching the sun climb gradually higher in the sky, its pale disk tracing slow circles that spiral upward day by day, month by month, year by year. The sun would never set, but neither would it remain stationary. Instead, it would perform a decades-long dance across the sky, reaching its highest point after 21 Earth years of continuous daylight, then beginning the equally long descent toward an autumn that wouldn't arrive for decades. The psychological impact of such seasons would be profound. Human cultures have always organized themselves around seasonal rhythms, planting and harvesting, festivals marking solstices and equinoxes, the psychological cycles of hope and dormancy that match the changing year. On Uranus, such rhythms would stretch beyond individual lifetimes, creating seasonal patterns that could only be understood across multiple generations. Yet there's also wonder in these extreme seasons. During Uranus's summer, the sun-facing pole experiences a perpetual Arctic summer, where the sun circles the sky without setting, gradually spiraling higher, and then lower as the decades pass, but never disappearing below the horizon. The light would have a quality unlike anything experienced on Earth, pale and steady, casting shadows that wheel slowly around objects as the sun traces its patient circles overhead. Meanwhile, the winter hemisphere endures a darkness so complete and prolonged that any weather systems there must operate entirely without solar heating, driven only by whatever warmth wells up from the planet's mysterious interior. This darkness isn't the familiar night that follows day on Earth, but a true seasonal night that stretches across decades, lit only by starlight and perhaps the faint glow of aurora dancing in the planet's offset magnetic field. The atmospheric consequences of this sideways orientation are only beginning to be understood. Unlike Earth, where seasonal temperature differences drive familiar weather patterns and wind systems, Uranus presents atmospheric scientists with a puzzle wrapped in an enigma. How do you model weather on a world where one hemisphere might be 30 degrees warmer than the other for decades at a time? How do atmospheric gases circulate when the primary source of energy, sunlight, arrives at such extreme angles? Picture the complexity of these atmospheric dynamics. On Earth, our weather systems are driven by the relatively simple pattern of equatorial heating and polar cooling, creating circulation patterns that meteorologists can predict with reasonable accuracy. On Uranus, the entire concept of equatorial and polar becomes fluid, changing meaning as the planet rolls through its orbit and different regions take their turn of facing the sun. During the long summer at one pole, that region becomes the warmest part of the planet, receiving continuous solar heating, while the opposite pole endures frigid darkness. This creates temperature gradients that run not from equator to pole as they do on Earth, but from one side of the planet to the other, gradients that shift and reverse over the course of Uranus's 84-year orbit around the Sun. Recent observations have revealed that Uranus's atmosphere does indeed show seasonal changes, but they unfold with the planet's characteristic patience. Bright clouds that appear in one hemisphere might persist for years before gradually fading, while temperature differences between the sunlit and shadowed regions create pressure gradients that drive winds in patterns completely unlike those on any other world. Some atmospheric models suggest that these extreme seasonal differences might create circulation patterns that are essentially unique in the solar system, weather systems that exist nowhere else, because no other world combines Uranus's particular size, composition, and sideways orientation. The cultural impact of Uranus's sideways nature extends beyond science into the realm of symbolism and meaning. In many human traditions, the concept of cosmic order depends on things having proper orientations, up and down, north and south, the reliable progression of seasons and celestial cycles. Uranus challenges these comfortable assumptions, presenting us with a world where the very foundations of spatial orientation become fluid and uncertain. Ancient cultures often interpreted unusual celestial behavior as omens or signs of cosmic disturbance. If they had been able to see Uranus's true nature, its sideways spin might have been viewed as a symbol of worlds turned upside down, of natural order disrupted by forces beyond human understanding. Even today, there's something unsettling about a planet that refuses to follow the rules, that rolls through its orbit in defiance of what seems like cosmic common sense. In modern art and literature, the concept of the sideways world has become a metaphor for perspectives that challenge conventional thinking. Like Uranus itself, These works suggest that truth sometimes requires us to abandon our comfortable assumptions about which way is up and how things should be oriented. The planet becomes a symbol of the value of seeing familiar things from radically different angles. The sideways world also speaks to themes of resilience and adaptation. Whatever knocked Uranus onto its side billions of years ago was clearly a traumatic event that might have destroyed a less robust world entirely. Yet Uranus endured, continuing to orbit the Sun and maintain its retinue of moons and rings despite, or perhaps because of, its unusual orientation. There's a lesson there about finding stability even after the most disruptive changes, about creating new kinds of order when the old rules no longer apply. The moons of Uranus add another layer to the sideways story. These worlds, bearing names like Titania, Oberon and Miranda from Shakespeare's plays, orbit in the plane of their parent planet's tilted equator, creating a satellite system that circles Uranus like the spokes of a slowly turning wheel. During certain parts of Uranus's orbit, these moons appear to dance up and down as seen from Earth, their orbits appearing nearly edge-on, as the planet's sideways orientation creates perspectives impossible for any other planetary system. As we contemplate the sideways world rolling through the outer darkness, there's something both humbling and inspiring about its defiance of conventional planetary behavior. Uranus reminds us that the universe doesn't arrange itself according to human expectations or comfortable assumptions about how things should work. It operates according to its own logic, shaped by events and processes that stretch across timescales we can barely comprehend. The extreme axial tilt that makes Uranus unique among the planets also makes it a laboratory for understanding how worlds can adapt to extraordinary circumstances. Its decades-long seasons and offset magnetic field provide natural experiments in planetary physics that we could never create artificially. In studying this sideways world, we learn not just about Uranus itself, but about the fundamental processes that shape all planets, and the remarkable diversity of ways that worlds can exist. As Uranus continues its slow roll through the cosmic deep, it carries with it the memory of whatever ancient catastrophe knocked it sideways, written in the tilt of its axis and the strange rhythms of its seasons. It's a world that has learned to find its own kind of stability in what might seem like perpetual imbalance, creating new forms of order from what was once chaos. And yet, for all its sideways spinning and upside-down seasons, perhaps the most mysterious thing about Uranus isn't how it moves through space, but how it appears to our eyes, or rather, how it doesn't appear, presenting an almost featureless face to the cosmos that hides secrets we're only beginning to understand. Imagine meeting someone whose face reveals absolutely nothing of their inner life. No smile lines to hint at joy, no furrows to suggest worry, no expressions that betray emotion or thought. They sit across from you in perfect stillness, their features as smooth and unmarked as fresh snow, offering no clues about the stories that might be unfolding behind their eyes. This is the puzzle that Uranus presents to anyone who turns a telescope toward the outer solar system, a world that has perfected the art of keeping secrets behind a mask of ethereal uniformity. From the time of Herschel's discovery until the present day, Uranus has worn this same enigmatic expression, presenting itself to observers as a pale blue-green disk, so featureless it almost seems unreal. Where Jupiter storms across telescopic views with bands and swirls that speak of atmospheric violence, and where Saturn glows with subtle zones and belts that hint at hidden complexities, Uranus maintains an almost supernatural serenity. It's as if the planet exists in a state of perpetual meditation, its atmosphere so still and uniform that early observers sometimes wondered if they were looking at a world at all, or merely at some cosmic optical illusion. The disappointment felt by generations of astronomers gazing at this bland face speaks to something deeply human about our expectations of cosmic drama. We want our planets to perform for us, to display their personalities with the bold strokes of obvious weather patterns and visible atmospheric structure. When Jupiter's great red spot rages for centuries, clearly visible even through modest backyard telescopes, it satisfies our hunger for spectacle. When Mars shows off its polar caps and seasonal dust storms, it behaves like a proper planet should, dynamic, changeable, willing to reveal its moods to patient observers. Uranus, by contrast, seems almost deliberately reticent, as though it has chosen to keep its atmospheric secrets locked away behind walls of uniformity. This reticence has shaped its cultural perception in ways that reach far beyond astronomy. In the early days of science fiction, when writers were populating the solar system with exotic worlds and alien civilizations, Uranus often received short shrift, dismissed as the boring planet that merited little more than a way station on journeys to more dramatic destinations. Yet there's something profoundly mysterious about this very blandness, something that speaks to depths hidden beneath apparent simplicity. Picture the surface of a deep mountain lake on a windless day, perfectly smooth, reflecting nothing but sky, giving no hint of the complex currents and hidden depths that lie beneath its mirror-like surface. This is the kind of mystery that Uranus embodies, not the obvious drama of surface spectacle, but the more subtle enigma of what might be concealed behind apparent calm. The colour itself carries stories written in the delicate language of light and chemistry. That ethereal blue-green hue that characterises Uranus comes from methane molecules floating high in the planet's atmosphere like cosmic artists working with palettes of absorption and reflection. These simple compounds, just carbon atoms cradled by hydrogen, have developed a peculiar taste for red light, devouring the warm wavelengths of the solar spectrum, while allowing the cooler blues and greens to escape back into space. It's the same basic principle that paints Earth's skies blue, but taken to atmospheric extremes that create colours unlike anything in our terrestrial experience. The methane molecules dance in sunlight that has travelled nearly 2 billion miles to reach them, each one acting like a tiny filter that removes specific wavelengths from the solar rainbow. The light that finally escapes back to our telescopes has been purified of its reds and oranges, leaving behind only those ethereal blues and greens that make Uranus appear like a world carved from celestial jade. But even this celestial artistry holds its own mysteries. Neptune, Uranus's distant cousin, carries roughly the same proportion of methane in its atmosphere, yet it blazes with a vivid, jewel-like intensity that makes Uranus appear washed out by comparison. It's as if someone adjusted the cosmic colour saturation just as the light reached Uranus, leaving it perpetually bathed in the muted tones of dawn rather than the full intensity of daylight. The reason for this difference remains hidden in the atmospheric chemistry of these ice giants, another secret that the featureless world keeps to itself. Descending through the layers of Uranus's atmosphere would be like sinking through veils of increasingly substantial air, each layer revealing new chapters in the planet's atmospheric story. Near the top, where the methane molecules perform their light-filtering dance, the atmosphere is thin enough that you could almost imagine breathing it, if only it weren't composed of hydrogen and helium instead of the oxygen-nitrogen mixture that fills earthly lungs. Deeper down, the atmosphere thickens gradually, like descending through layers of silk that become progressively more substantial. The temperature here follows patterns that confound atmospheric scientists. This distant world, receiving only a fraction of the solar energy that warms the inner planets, maintains temperatures that are surprisingly uniform from pole to pole, season to season. It's as if the entire atmosphere has learned to share heat with the efficiency of a perfectly designed heating system, distributing every precious calorie of solar warmth throughout the entire planetary envelope. The most puzzling aspect of Uranus's atmospheric story lies in what's missing rather than what's present. Unlike Jupiter, Saturn, and Neptune, all of which glow with internal warmth left over from their formation billions of years ago, Uranus radiates almost no excess energy into space. It's as if some cosmic thief has stolen the planet's inner fire, leaving behind a world that can only reflect the pale, distant warmth of the sun, rather than contributing its own heat to the cosmic darkness. Picture a house where the furnace has failed on the coldest night of winter. Without that internal source of warmth, the rooms that should be cozy and inviting become still and cold, their very stillness a testament to the absence of the energy that once gave them life. This is Uranus, a world that has somehow misplaced the primordial heat that should drive dynamic atmospheric circulation, leaving behind an atmosphere of almost crystalline calm. This thermal mystery might explain the planet's enigmatic serenity. On worlds with strong internal heat sources, warm gases rise from the interior, while cooler material sinks to take their place, creating the convection patterns that drive dramatic weather systems. Without this internal engine, Uranus's atmosphere settles into a state of minimal activity, sustained only by the weak energy of distant sunlight, and whatever heat might occasionally well up from the planet's mysterious depths. Yet even in this apparent stillness, subtle dramas unfold for those patient enough to watch and sensitive enough to detect them. The Hubble Space Telescope, with its exquisite sensitivity to variations in light and colour, has occasionally spotted bright clouds appearing in Uranus's atmosphere, like morning mist forming over still water. These ephemeral features appear and fade over timescales ranging from hours to months, hinting at atmospheric processes that operate according to rhythms we're only beginning to understand. Some of these rare clouds seem to be associated with the planet's extreme seasonal cycles, appearing as different regions of the atmosphere gradually transition from decades of winter darkness into the pale warmth of Uranian spring. Others might be driven by processes we haven't yet identified, perhaps chemical reactions triggered by solar radiation, or thermal plumes rising from depths we can't directly observe. The challenge of studying Uranus's bland atmosphere has pushed astronomers to develop new techniques for extracting information from the subtlest variations in planetary light. Like archaeologists learning to read stories from the faintest marks in ancient clay, atmospheric scientists have learned to detect seasonal changes, chemical compositions, and circulation patterns from variations in brightness too subtle for the eye to perceive. Spectroscopy, the analysis of how different wavelengths of light are absorbed or reflected by atmospheric gases, has become a kind of cosmic chemistry, set that allows us to identify molecules and measure temperatures in regions we may never visit directly. Through these techniques, we've learned that Uranus's atmosphere contains not just hydrogen, helium, and methane, but also traces of water vapor, ammonia, and hydrogen sulfide, compounds that paint a complex picture of atmospheric chemistry operating under conditions found nowhere on Earth. The temperature profile that emerges from these studies reads like a story written in the language of atmospheric physics. In the highest regions of Uranus's atmosphere, where the air is thin enough that molecules rarely collide, temperatures can plunge to minus 224 degrees Celsius, cold enough to freeze nitrogen solid and turn familiar gases into exotic ices. Yet deeper in the atmosphere, where pressure begins to compress the gas into denser configurations. Temperatures gradually rise, following patterns that reflect the delicate balance between solar heating and the planet's minimal internal energy. The formation of atmospheric layers and hazes adds another chapter to this celestial chemistry story. High above Uranus, where solar radiation is intense enough to break apart methane molecules, photochemical reactions create a variety of organic compounds that exist nowhere in terrestrial experience. These molecules, forged in the cold vacuum of the outer solar system, condense into hazes and particles that affect how the planet's atmosphere scatters and absorbs light. The seasonal nature of these processes creates atmospheric poetry written across decades rather than months, as different regions of Uranus slowly rotate from winter into summer, transitions that unfold over timescales longer than human careers. The intensity and distribution of photochemical activity gradually shifts. Some atmospheric layers might thicken during the long summer, while others fade during the equally extended winter, creating variations so subtle they require years of patient observation to detect. In human culture, the concept of the blank face or empty canvas has carried profound symbolic weight across centuries of art and literature. The minimalist aesthetic, the power of empty space, the eloquence of what's left unsaid, represents a philosophical approach to beauty that finds meaning in restraint rather than excess. Uranus embodies this aesthetic on a planetary scale, demonstrating that cosmic beauty doesn't always announce itself with dramatic flourishes, but can exist in the spaces between obvious features. Modern art movements have taught us to appreciate the beauty of subtlety, the way negative space can be as powerful as bold strokes, the manner in which absence can speak as loudly as presence. Uranus challenges us to apply this same aesthetic philosophy to our understanding of planetary atmospheres. Perhaps the planet's featureless appearance isn't a flaw, but a different kind of perfection, the visual equivalent of a meditation on stillness, a cosmic statement about the power of understatement. The scientific challenge of studying such a subtly beautiful world has led to innovations that extend far beyond planetary astronomy. The techniques developed to detect and analyze Uranus's faint atmospheric variations have applications in studying exoplanet atmospheres, analyzing climate change on Earth, and understanding atmospheric processes throughout the solar system. In learning to read the whispered signals hidden in Uranus's bland appearance, we've developed tools for interpreting atmospheric behavior across a wide range of cosmic environments. The patience required to study Uranus's atmospheric changes mirrors the patience required for many forms of deep understanding. Like master craftspeople who spend decades perfecting subtle techniques, or musicians who learn to hear the spaces between notes as clearly as the notes themselves, atmospheric scientists studying Uranus have learned to find profound meaning in the subtlest variations. They've discovered that what appears featureless to casual observation actually contains layers of complexity that reveal themselves only to the most patient and sensitive investigation. As we contemplate this pale, enigmatic world spinning through the outer darkness, there's something deeply moving about its atmospheric restraint. In an age of constant stimulation and obvious spectacle, Uranus reminds us that some kinds of beauty require quiet attention to appreciate fully. Its atmospheric serenity speaks to anyone who's ever found peace in still water, blank paper, or the contemplative silence that follows a snowfall. The planet's uniform appearance also serves as a reminder that our solar system contains worlds that operate according to logic completely different from our earthly experience. Where Earth's atmosphere churns with weather systems driven by solar heating and rotation, where Mars displays dramatic seasonal changes and where the gas giants storm with obvious violence, Uranus has found its own path, a way of existing that prioritizes subtlety over drama, patience over urgency. Tonight, as Uranus continues its slow roll through the cosmic deep, its featureless atmosphere maintains the same enigmatic calm it has displayed for centuries of human observation. Somewhere in those bland, beautiful layers, processes unfold that we're only beginning to understand. Chemical reactions proceeding at their own pace, thermal currents flowing according to patterns we haven't yet learned to read, and perhaps even weather systems so subtle they exist at the very limit of detectability. The methane molecules continue their ancient dance with sunlight, filtering red wavelengths and releasing blues and greens in the same patient rhythm they've maintained since the solar system's youth. The rare clouds that occasionally appear in those ethereal skies form and fade according to schedules written in the deep physics of atmospheric circulation, visible only to our most sensitive instruments and most persistent observers. In its atmospheric mysteries and sublime restraint, Uranus stands as a reminder that the universe contains forms of beauty we're only beginning to appreciate. Not the obvious spectacle of stormy giants, but the subtler elegance of worlds that whisper their secrets rather than shouting them, that reveal their complexity only to those patient enough to look beyond surface appearances and wise enough to find profound meaning in the spaces between obvious features. Yet even as we struggle to read the atmospheric secrets written in that featureless face, Uranus holds another surprise entirely, a discovery that came not through careful study of the planet itself, but through the serendipitous observation of a star that happened to pass behind it on a March night in 1977, revealing that even the most uniform worlds can wear hidden ornaments of shadow and starlight. Picture a night when the universe decides to play a quiet magic trick, offering up a secret that has been hidden for billions of years. March 10th, 1977, began like countless other nights in the history of astronomy. Telescopes pointing skyward, scientists hunting for answers to questions that had puzzled them for decades. But by dawn, everything we thought we knew about planetary rings had changed forever, revealed not through careful planning or systematic search, but through the kind of cosmic accident that makes you believe the universe has a sense of timing. High above the Indian Ocean, a modified C-141 cargo plane called the Kuiper Airborne Observatory traced lazy circles through the stratosphere. Inside its aluminum belly, astronomers huddled around instruments that had been designed to peer through the thin air at 11 kilometers altitude, above most of the water vapor that normally clouds our view of distant worlds. They were chasing shadows, literally, waiting for Uranus to pass in front of a star called SA-0158687, an event that would last only minutes, but might reveal secrets about the planet's atmosphere and size. The technique they were using, stellar occultation, reads like something from a cosmic detective story. When a planet passes between Earth and a distant star, the starlight must travel through the planet's atmosphere before reaching our telescopes. Any gases, hazes, or atmospheric layers will leave their fingerprints in the starlight, dimming it slightly, or changing its color in ways that reveal the chemical composition and structure of that distant world's air. It's like holding a candle behind a piece of frosted glass and studying the shadows to understand what lies between the flame and your eye. But as the astronomers aboard the Kuiper Airborne Observatory watched their instruments on that March night, something unexpected began to unfold. The star didn't simply dim smoothly as Uranus approached. Instead, it flickered. 5 brief shadows swept across the star's light in the minutes before Uranus itself blocked the stellar beacon, and then 5 more shadows appeared on the other side, after the planet had passed and the star should have returned to its normal brightness. Imagine the mixture of excitement and confusion that must have filled the aircraft's cramped cabin. These weren't random instrumental glitches or atmospheric turbulence. The shadows were too symmetrical, too precisely timed. Something was orbiting Uranus. Something so dark and narrow that it had remained completely invisible to every telescope that had ever been pointed at the distant planet. In the space of a few minutes, Uranus had transformed from a lonely, featureless world into a ringed planet. The revelation sent shockwaves through the astronomical community with the force of a small earthquake. For nearly 400 years since Galileo first noticed Saturn's mysterious handles through his primitive telescope, rings had been Saturn's unique signature in the solar system. Saturn was the ringed planet, as distinctive and singular as Jupiter's great red spot or Mars's rusty deserts. The possibility that other worlds might wear their own delicate ornaments of ice and rock had never seriously been considered. Yet here was the evidence, written in the language of shadows and starlight. Uranus possessed not one ring, but at least 5, slender hoops of material so dark they reflected almost no sunlight, so narrow they could never have been detected by direct observation. They were like pencil lines drawn around the planet, invisible except when they happened to cross in front of something bright enough to reveal their presence through the shadows they cast. The rings themselves tell a story written in darkness and emptiness. Unlike Saturn's brilliant, icy rings that sparkle like cosmic jewelry when sunlight strikes them, Uranus's rings are composed of material so dark it absorbs light like cosmic charcoal. The particles that make up these rings reflect only about 2% of the sunlight that hits them, darker than fresh asphalt, darker than the soot that collects in a chimney. They're made of organic compounds, complex carbon-based molecules that have been cooked by radiation and cosmic rays into materials that seem to swallow light rather than reflect it. Picture trying to see a black cat in a coal cellar at midnight, and you begin to understand why these rings remained hidden for so long. They orbit Uranus in the plane of its tilted equator, which means that from Earth's perspective, they're sometimes edge-on and nearly invisible, sometimes tilted at angles that would make them visible if only they weren't so impossibly dark. It's as if someone designed the perfect system for hiding rings around a planet, make them narrow, make them dark, and tilt them at angles that change constantly as the planet rolls through its sideways orbit. The discovery also revealed something profound about the nature of planetary ring systems themselves. Before 1977, astronomers assumed that rings were rare, perhaps unique to Saturn. The rings around Uranus suggested instead that ring systems might be common features of giant planets, delicate structures that form and evolve according to processes we were only beginning to understand. The cultural impact of the discovery rippled far beyond the scientific community. Saturn had been the ringed planet in human consciousness for centuries, featured in countless science fiction stories, educational materials, and popular depictions of the solar system. Suddenly, the cosmos had become more complex, more varied, less predictable. If Uranus could hide rings for hundreds of years, what other secrets might the outer planets be keeping? The accidental nature of the discovery also spoke to something beautiful about the process of scientific exploration. The most revolutionary findings often come not from seeking specific answers, but from maintaining the kind of careful attention that allows unexpected phenomena to reveal themselves. The astronomers aboard the Kuiper Airborne Observatory weren't looking for rings, they were studying atmospheric structure. Yet their willingness to notice when observations didn't match expectations opened a door to an entirely new understanding of planetary systems. As more observations accumulated in the months and years following the discovery, the ring system revealed additional layers of complexity. The initial 5 rings grew into a family of at least 11 distinct components, each with its own characteristics and orbital dynamics. Some rings were perfectly circular, others slightly elliptical. Some were narrow and sharply defined, others broad and diffuse. The most prominent ring, designated Epsilon, proved to be variable in width, broader in some parts of its orbit than others, as if something was squeezing and stretching it like a cosmic accordion. The discovery of shepherding moons added another chapter to the ring story. Small satellites, most no larger than a few kilometers across, were found orbiting just inside and outside some of the rings, their gravitational influence apparently keeping the ring particles confined to their narrow lanes. It was like discovering that cosmic traffic cops were maintaining order among the orbiting debris, preventing the particles from wandering away or spreading out into broader, more diffuse structures. These shepherding satellites revealed that ring systems are dynamic, evolving structures rather than static ornaments. The gravitational dance between moons and ring particles creates resonances and perturbations that sculpt the rings into complex patterns. Some particles are nudged into slightly different orbits, others are swept up by the shepherding moons, and new material might occasionally be added when meteoroids strike the small moons and blast debris into orbit around the planet. The rings also provided new insights into the violent history of the Uranian system. The dark, organic-rich particles that make up the rings might be the remnants of small moons that were shattered by impacts billions of years ago. The carbon-based compounds could be the remains of ancient comets that wandered too close to Uranus and were torn apart by tidal forces, their fragments gradually spreading into the narrow bands we observe today. There's something poetic about rings that can only be seen in silhouette, revealed not by their own light, but by the shadows they cast across distant stars. They remind us that not all beauty announces itself boldly. Sometimes the most exquisite cosmic phenomena hide in darkness, waiting for exactly the right circumstances to reveal their presence. The rings of Uranus are like cosmic lace, delicate patterns traced in the void that become visible only when the universe arranges itself just so. The discovery also demonstrated the power of international collaboration in astronomy. The Kuiper Airborne Observatory was a joint project involving scientists from multiple institutions and countries, all working together to push the boundaries of what could be observed from Earth's atmosphere. The revelation of Uranus's rings became a shared triumph, celebrated in observatories and universities around the world as evidence of what could be accomplished when human curiosity and ingenuity worked in harmony. In the decades since their discovery, the rings of Uranus have continued to surprise astronomers with their complexity and variability. Some components have been observed to change in brightness over time, suggesting that the ring particles might be clumping together or spreading apart in response to forces we don't yet fully understand. Others seem to be evolving in real time, their structure shifting subtly from one observation to the next. The seasonal nature of Uranus's orientation adds another layer of mystery to its ring system. As the planet rolls through its 84-year orbit, different parts of the ring spend decades in sunlight, followed by decades in shadow. This extreme seasonal heating and cooling might affect the behavior of ring particles in ways that we're only beginning to explore. Some scientists speculate that the rings themselves might show seasonal variations, changing their structure or composition as different regions cycle through Uranus's extended seasons. The challenge of studying Uranus's rings from Earth also push the development of new observational techniques that have applications far beyond this single planetary system. The methods developed to detect and analyze these dark, narrow rings have been used to discover ring systems around other distant objects and to study the structure of planetary atmospheres throughout the solar system. As we contemplate these hidden rings spinning silently around their tilted planet, there's something deeply moving about their secret existence. For billions of years, they traced their narrow paths through the darkness, unseen and unsuspected, waiting for that perfect moment when human curiosity and cosmic geometry would align to reveal their presence. They remind us that the universe still holds secrets in plain sight, wonders that have been there all along, simply waiting for us to develop the tools and techniques necessary to recognize them. The rings of Uranus also speak to the democratic nature of cosmic beauty. Not every planetary ornament needs to sparkle like Saturn's brilliant ice rings to be worthy of wonder. Sometimes elegance lies in subtlety, in structures so perfectly adapted to their environment that they become nearly invisible, revealed only through the most careful and patient observation. Tonight, as Uranus rolls through the outer darkness with its family of dark rings spinning around its tilted equator, those rings continue their ancient dance, casting shadows we cannot see across stars too distant for our eyes to find. They are there nonetheless, cosmic calligraphy written in the void, a reminder that even the most unremarkable-looking planets can wear jewelry made of darkness and dreams. But the rings, for all their subtle beauty, are not the only hidden treasures orbiting this sideways world. Circling beyond the narrow bands of dark particles, a family of moons traces more distant paths through space, each one carrying its own story of ice and rock, poetry and physics, bearing names that would have made the bard himself smile with recognition. Imagine opening a book of Shakespeare's plays and finding that the characters have somehow escaped their printed pages to dance through the darkness of space, each one carrying the essence of their earthly drama into the cosmic void. This is the gift that William Herschel's son John gave to astronomy when he named the major moons of Uranus, not after the usual suspects from Greek and Roman mythology, but after the sprites and spirits, the noble lords and tragic heroes who populate the bard's most beloved works. Titania and Oberon, the fairy king and queen from A Midsummer Night's Dream, circle Uranus in a stately dance befitting their royal status, the largest satellites in this sideways kingdom. Umbriel carries the melancholy weight of Alexander Pope's Rape of the Lock, a dark moon whose name means shadow, and whose surface seems to wear that darkness like a mourning cloak. Ariel sparkles with the ethereal energy of the Tempest's air spirit, while Miranda, poor innocent Miranda from that same play, bears a surface so violently disrupted it looks as though some cosmic Caliban has been at work reshaping her face. There's something deeply poetic about this naming convention, this decision to populate the outer solar system with characters from literature rather than gods from ancient pantheons. It suggests that by the time humanity had developed telescopes powerful enough to spot these distant worlds, we had moved beyond simply mapping the cosmos. We were beginning to see it as a place where human stories and cosmic realities could interweave, where the boundaries between art and science might dissolve in the patient light of distant suns. The moons themselves orbit Uranus in the plane of its tilted equator, which means they follow the planet's sideways orientation through space. Picture a spinning coin that's been knocked over onto its side. The moons trace paths around Uranus like the spokes of a slowly turning wheel, their orbits perpendicular to those of almost every other satellite system in the solar system. It's a family portrait taken at an impossible angle, a reminder that even in the cosmos there are no rules so fundamental that they can't be broken by the right catastrophe. Titania, the largest of Uranus's moons, stretches nearly 1,600 kilometers across, roughly half the diameter of our own moon, but still substantial enough to have shaped itself into a proper sphere under the patient pull of its own gravity. Her surface tells a story of ancient violence written in the language of cracks and canyons that stretch for hundreds of kilometers across ice and rock that hasn't felt the warmth of close sunlight since the solar system's youth. Imagine standing on Titania's frozen plains, if such a thing were possible. The horizon would curve away under a salmon-coloured sky so thin it's barely there at all, while overhead the pale blue-green disk of Uranus would hang motionless in the star-filled darkness. The parent planet would never move from its position in Titania's sky, locked in place by the same tidal forces that keep our moon forever showing us the same familiar face. But unlike our moon's view of Earth as a dynamic blue marble, Titania's residents would see a world that reveals almost nothing of its secrets, a featureless sphere that offers no hints of the atmospheric mysteries hidden beneath its uniform surface. The cracks that scar Titania's face speak of a moon that has experienced its own version of growing pains. These aren't the random impacts that pepper most airless worlds with craters, but systematic fractures that suggest the moon's interior once expanded, perhaps when underground oceans froze and swelled, splitting the surface like ice forming in a water pipe. The largest of these canyons, Messina Chasma, stretches nearly 1,500 kilometers across Titania's surface, a wound in the moon's face that dwarfs Earth's Grand Canyon and tells of forces that operated on scales difficult for terrestrial minds to grasp. Oberon, Titania's slightly smaller companion, wears the scars of its violent history more subtly. Its ancient surface is peppered with craters that have remained largely unchanged for billions of years, a fossil record of the early solar system when massive impacts were common and worlds were still settling into their final configurations. Yet even Oberon shows hints of internal activity in its past, bright rays of material extending from some of its youngest craters, evidence that this seemingly dead world once had enough geological vitality to resurface portions of its terrain. But it's Miranda that truly captures the imagination with her chaotic patchwork geology. At only 500 kilometers across, she's the smallest of Uranus's major moons, yet her surface displays some of the most bizarre and dramatic landscapes found anywhere in the solar system. Imagine a world that looks as though it was assembled from spare parts, ancient, heavily cratered terrain abruptly giving way to regions of parallel ridges and grooves that seem to follow no earthly logic, all stitched together by scarps and cliffs that tower kilometers above the surrounding plains. The geological chaos on Miranda's surface has earned her the nickname Frankenstein Moon among planetary scientists, a world that appears to have been taken apart and reassembled, possibly multiple times, by forces that defy easy explanation. Some regions show the familiar, random peppering of impact craters that characterizes most airless worlds. Others display the parallel ridges and smooth plains, typical of worlds where internal geological processes have resurfaced the terrain. Still others show fractured, jumbled landscapes that look like nothing so much as broken ice flows, refrozen into impossible configurations. The leading theory for Miranda's bizarre appearance involves a process almost too violent to imagine. Perhaps this small moon was once shattered completely by a massive impact, its fragments scattered through space, before slowly reassembling under the patient pull of mutual gravitation. The different types of terrain we see today might represent pieces of the original Miranda, mixed with material that was melted and reshaped during the reassembly process, a cosmic jigsaw puzzle where some pieces came from the original picture and others were created entirely new. Picture the aftermath of such a cataclysm unfolding over millions of years. Chunks of the original Miranda, ranging from boulders to pieces hundreds of kilometers across, would have drifted slowly back together, each collision adding another layer to the growing pile of debris. The largest fragments might have retained their original surface features, while smaller pieces would have been ground down and mixed together into the smooth plains and parallel ridges we observe today. The result is a world that carries the memory of its own destruction and resurrection written into every cliff and canyon. Ariel, despite sharing her name with Shakespeare's airy sprite, is actually one of the most geologically active-looking worlds in the Uranian system. Her surface shows clear evidence of past tectonic activity, fault systems and rift valleys that suggest this moon once experienced the kind of internal heating that can drive geological processes for millions of years. The smooth plains that cover portions of Ariel's surface speak of relatively recent resurfacing events, times when internal heat melted subsurface ice and allowed it to flow like lava across the landscape, erasing older impact craters and creating the youngest terrain found on any of Uranus's major moons. The source of this internal heating remains one of the puzzles of the Uranian system. These moons are far too small to retain significant heat from their formation billions of years ago, and they're too distant from Uranus to experience the kind of tidal heating that keeps some of Jupiter's and Saturn's moons geologically active. Yet the evidence written in Ariel's surface features suggests that something provided enough energy to drive geological processes long after these worlds should have frozen solid. Umbriel presents the opposite extreme, a world so dark and ancient-looking that it seems to absorb light like a cosmic sponge. Named after the melancholy gnome from Pope's poem, Umbriel lives up to her literary heritage with a surface that reflects only about half as much sunlight as her companions. The reasons for this darkness remain mysterious. Perhaps Umbriel's surface is covered with organic compounds that have been darkened by eons of radiation, or maybe the moon has somehow avoided the geological processes that have brightened and refreshed the surfaces of her sisters. Standing on Umbriel's darkened plains would be like exploring the surface of charcoal by starlight. The distant sun would provide only the faintest illumination, while the pale glow of Uranus would cast everything in subtle shades of blue and grey. It would be a world of whispered colours and gentle shadows, where the drama of geological processes has given way to the quiet patience of deep time. The discovery and study of these moons has been a gradual process stretching across more than 2 centuries. Herschel himself discovered the first 2, Titania and Oberon, in 1787, just 6 years after his accidental discovery of Uranus itself. Ariel and Umbriel followed in 1851, spotted by William Herschel using improved telescopes that could separate the faint dots of light from the glare of their parent planet. Miranda remained hidden until 1948, when Gerard Kuiper finally detected her dim glow using photographic techniques that allowed for the patient accumulation of light over long exposures. Each discovery expanded our understanding of the Uranian system and revealed new complexities in the architecture of this sideways world. The moons don't simply orbit randomly around Uranus. They're locked into intricate gravitational relationships with each other and with the planet's ring system. Some pairs of moons trace orbital resonances that keep them in precise mathematical relationships, never approaching too closely, but never drifting too far apart. These resonances help stabilize the entire satellite system and may play a role in maintaining the narrow structure of some of Uranus's rings. The Voyager 2 encounter in 1986 revolutionized our understanding of these distant worlds by providing the first close-up images of their surfaces. Until that moment, the moons of Uranus existed only as points of light in telescopes, their individual characteristics hidden by distance and the limitations of Earth-based observation. Voyager's cameras revealed worlds of startling diversity, each moon telling its own story of formation, evolution, and survival in the outer darkness. The seasonal nature of the Uranian system adds another layer of complexity to these moons' existence. As Uranus rolls through its 84-year orbit, each moon experiences decades-long seasons that dwarf any earthly cycle. For 21 years at a time, one hemisphere of each moon basks in continuous, albeit faint, sunlight, while the opposite hemisphere endures an equally long winter of perpetual darkness. The temperature differences created by these extreme seasons may drive subtle atmospheric processes and even geological activity that we're only beginning to understand. Some scientists speculate that the larger moons of Uranus might harbour subsurface oceans beneath their icy crusts, hidden seas kept liquid by the small amounts of internal heat generated by radioactive decay or tidal interactions. These theoretical oceans would be dark, cold places, far removed from the warm, sunlit seas of Earth, yet they might represent the most likely habitats for life in the Uranian system. The chemistry of these hidden waters, enriched by materials leached from the moon's rocky cores, could potentially support the kinds of simple organisms that thrive in Earth's deep ocean trenches. The literary names of Uranus's moons also remind us that science and art need not exist in separate spheres. The decision to draw names from Shakespeare and Pope rather than classical mythology reflects a recognition that human creativity and cosmic wonder can enhance each other. When we look at Miranda's fractured landscape, we might remember the innocent daughter in The Tempest, who marvelled at the brave new world that had such people in it. When we contemplate Titania's stately orbit around her tilted planet, we can imagine the fairy queen ruling over a domain far stranger than any forest near Athens. These moons continue their ancient dance through the darkness, carrying their literary names and geological stories through the cosmic deep. They remind us that even in the outer reaches of the solar system, worlds can be complex, dynamic, and full of surprises. Each one represents a different experiment in planetary formation and evolution, a different way that ice and rock can combine to create worlds that challenge our understanding of how satellites form and survive. As we contemplate these diverse worlds spinning through their sideways orbits around Uranus, we're reminded that the solar system's architecture is far more varied and wonderful than early astronomers could have imagined. The moons of Uranus don't simply provide companionship to their parent planet. They offer glimpses into processes and possibilities that extend far beyond our own earthly experience, carrying stories written in ice and stone across the patient darkness of space. Yet for all their individual character and literary charm, these moons and their parent planet represent something even more profound in our understanding of cosmic architecture. They belong to an entirely different category of world than the gas giants that dominate the outer solar system, ice giants whose very existence tells a story of planetary formation unlike anything we see in the inner system or among Jupiter's and Saturn's massive hydrogen-rich domains. Imagine trying to sort a collection of pearls by size and discovering that what you thought was a simple gradation from small to large actually contains two entirely different types of gems. Some formed in oysters, others crystallized in completely different processes that just happened to create similar shapes. This is what happened to our understanding of the outer planets when scientists began to peer beneath the surfaces of the giant worlds that patrol the cold frontiers of our solar system. For most of the 20th century, astronomers grouped Jupiter, Saturn, Uranus, and Neptune together under the simple banner of gas giants, massive worlds composed primarily of hydrogen and helium, like scaled-up versions of the Sun itself. They were the big planets, the heavy planets, the worlds that had grown large enough during the solar system's formation to capture and hold onto the light gases that made up the primordial solar nebula. It seemed like a natural classification, as obvious as grouping all the terrestrial worlds together based on their rocky, Earth-like compositions. But as our instruments grew more sensitive and our understanding of planetary formation deepened, cracks began to appear in this tidy classification. Uranus and Neptune, it turned out, were fundamentally different beasts than their larger cousins. Yes, they were giant planets, but calling them gas giants was like calling a whale a fish. Technically, they shared some obvious characteristics, but the deeper you looked, the more apparent it became that they belonged to an entirely different category of cosmic creature. The revelation began with mass and density measurements that didn't quite fit the expected patterns. Jupiter and Saturn, the true gas giants, are enormous but surprisingly light for their size, great balloons of hydrogen and helium that would actually float if you could find an ocean large enough to hold them. Uranus and Neptune, by contrast, pack much more material into smaller volumes. They're denser, more compressed, built from a fundamentally different recipe of cosmic ingredients. Picture slicing these worlds open like cosmic layer cakes, and the differences become even more striking. Jupiter and Saturn would reveal relatively simple structures, small rocky cores surrounded by vast envelopes of hydrogen and helium that make up most of their mass. They're essentially stars that never quite managed to ignite, worlds that captured so much of the solar nebula's raw material that their compositions mirror the Sun itself. Uranus and Neptune tell a more complex story written in ice and rock and exotic materials that exist nowhere in our earthly experience. Beneath their relatively thin atmospheric envelopes lies something far more substantial. Mantles composed of water, ammonia, and methane that have been compressed into strange states of matter by the immense pressures found deep within these worlds. At the centre, solid cores of rock and metal that may be more massive than Earth itself, buried beneath thousands of kilometres of compressed ices that behave more like molten metal than anything we'd recognise as water. The term ice giant captures something essential about these worlds that gas giant never could. Ice, in the vocabulary of planetary science, doesn't just mean frozen water. It refers to any compound that condenses into solid form in the cold outer reaches of the solar system. Water ice, yes, but also ammonia ice, methane ice, and dozens of other compounds that remain liquid or gaseous near the Sun, but freeze solid in the deep cold beyond the asteroid belt. These ices tell the story of where and how Uranus and Neptune formed. In the early solar system, the region where they coalesced was cold enough for water to freeze, but still warm enough that the lightest gases, hydrogen and helium, remained relatively scarce. As a result, the growing planets built themselves primarily from heavier materials, rock, metal, and the ices of various compounds that could survive in the temperatures found at their orbital distances. By the time Uranus and Neptune had grown large enough to begin capturing significant amounts of hydrogen and helium from the surrounding nebula, much of that primordial gas had already been swept away by the young Sun's powerful stellar winds. They managed to accumulate some atmospheric hydrogen and helium, but not nearly enough to transform them into the hydrogen-dominated giants that Jupiter and Saturn became. The formation story becomes even more complex when we consider the possibility that these ice giants didn't form where we find them today. The Nice model of solar system evolution suggests that all 4 giant planets underwent a period of dramatic migration during the solar system's youth, a cosmic game of musical chairs that saw worlds wandering far from their birth locations before settling into their current orbits. Picture the early solar system as a construction site where the blueprints kept changing. Uranus and Neptune might have begun their lives much closer to the Sun, perhaps in the region between Jupiter and Saturn, where building materials were more abundant. Gravitational interactions between the growing giants could have flung them outward into the cold outer reaches, like stones thrown from a cosmic slingshot. This migration would have been a violent, chaotic process. As the ice giants moved outward, they would have ploughed through the outer solar system's population of small bodies, comets and asteroids and planetary building blocks that had been quietly orbiting in the cold outer reaches. Some of this material would have been flung entirely out of the solar system, while other pieces would have been scattered into new orbits, creating the populations of objects we see today in the Kuiper Belt and scattered disk. The evidence for this ancient migration is written in the current architecture of the outer solar system. The distribution of objects beyond Neptune bears the gravitational fingerprints of worlds that have moved through these regions, stirring and scattering the inhabitants like a cosmic mixing bowl. Computer simulations that include planetary migration can reproduce many features of the solar system that remain mysterious if we assume the planets formed in their current locations. The ice giant classification also helps explain some of the puzzling characteristics that make Uranus and Neptune different from their larger cousins. Their unusual magnetic fields, for instance, make much more sense when you consider that these worlds generate their magnetism not in metallic cores like the terrestrial planets, but in the electrically conductive layers of their compressed ice mantles. The strange tilts and offsets of their magnetic fields reflect the exotic conditions found in these high-pressure, high-temperature oceans of superionic ice. The atmospheric differences between gas giants and ice giants also become clearer when viewed through the lens of their different compositions and formation histories. Jupiter and Saturn, with their massive hydrogen envelopes and strong internal heat sources, support dynamic weather systems driven by convection from their hot interiors. Uranus and Neptune, with less internal heat and more complex atmospheric chemistry, display different patterns of circulation and storm formation. The concept of ice giants has profound implications for our understanding of planetary systems beyond our own solar system. As we discover thousands of exoplanets orbiting other stars, we find that Neptune-sized worlds are among the most common types of planets in the galaxy. These discoveries suggest that the ice giant formation process is not unusual, but rather represents one of the most successful strategies for building planets in the cold outer regions of stellar systems. Many of the exoplanets we've discovered are super-Earths or mini-Neptunes, worlds larger than Earth but smaller than Neptune that may represent variations on the ice giant theme. Understanding how Uranus and Neptune formed and evolved provides crucial insights into the processes that create these intermediate-sized worlds, which appear to be far more common in the galaxy than planets like Jupiter and Saturn. The ice giant classification also changes how we think about habitability and the potential for life in planetary systems. While the surfaces of these worlds are far too cold and the pressures far too extreme to support life as we know it, their moons present more intriguing possibilities. The same processes that created the complex internal structures of ice giants might also operate in large moons, potentially creating subsurface oceans that could harbour microbial life. In human culture, the recognition of ice giants as a distinct class of worlds represents part of a larger evolution in how we classify and understand the cosmos. Early astronomers divided the universe into simple categories: fixed stars and wandering planets, celestial and terrestrial realms. As our knowledge has grown, these classifications have become increasingly sophisticated and nuanced. The journey from gas giant to ice giant mirrors similar transitions in other sciences. Biology has moved from simple categories of plant and animal to complex evolutionary trees that recognize the deep relationships between all living things. Chemistry has evolved from the four classical elements to the periodic table's elegant organization of atomic structure. Astronomy continues this tradition, refining its classifications as new discoveries reveal previously hidden complexities. There's something poetic about worlds made primarily of ice existing in the warm thoughts of beings made primarily of water. The same H2O molecules that flow through our bodies and fill our oceans also make up significant portions of these distant worlds, though compressed and heated into states so exotic, they bear little resemblance to any earthly water. In a sense, we are connected to these ice giants through the fundamental chemistry of existence itself. The seasonal behavior of ice giants adds another layer to their unique character. Because their internal heat sources are minimal compared to the true gas giants, Uranus and Neptune are more sensitive to the weak variations in solar heating that occur across their long orbital periods. This creates the possibility of slow atmospheric changes that unfold over decades or centuries, seasonal patterns that dwarf anything experienced on the terrestrial planets. The study of ice giants has also pushed the development of new theoretical models and computational techniques. The extreme conditions found in their interiors, temperatures of thousands of degrees and pressures millions of times greater than Earth's surface, can't be reproduced in earthly laboratories. Instead, scientists must rely on sophisticated computer simulations and theoretical physics to understand how matter behaves under such exotic conditions. These models have applications far beyond planetary science. The same techniques used to understand the interiors of ice giants help us model the behavior of matter in white dwarf stars, the cause of brown dwarfs and other extreme environments throughout the universe. In studying Uranus and Neptune, we develop tools for understanding a much broader range of cosmic phenomena. The ice giant classification also highlights the importance of understanding planets as systems rather than isolated objects. The unusual characteristics of Uranus, its extreme axial tilt, its offset magnetic field, its lack of internal heat, make more sense when viewed as the interconnected consequences of its ice giant nature and its violent formation history. The planet's current state reflects billions of years of evolution as an ice-rich world in the outer solar system. As we look toward future exploration of the outer solar system, the ice giant classification guides our mission planning and scientific priorities. Understanding that Uranus and Neptune are fundamentally different from Jupiter, and Saturn helps us design instruments and experiments specifically tailored to answer questions about these unique worlds. The mysteries they present, from their tilted magnetic fields to their featureless atmospheres, require approaches different from those we'd use to study gas giants. Tonight, as Uranus continues its slow roll through the darkness, it carries with it the story of an entirely different approach to planetary construction, a world built from ice and rock and exotic materials, shaped by processes that created something neither terrestrial nor truly gaseous, but occupying its own unique category in the cosmic bestiary. It reminds us that the universe is far more creative in its planetary architectures than our early classifications suggested, capable of building worlds that challenge our assumptions about how planets should form and behave. And yet, for all that we've learned about Uranus through theoretical models and distant observations, there remains something profound about the single close encounter that gave us our most detailed glimpse of this ice giant, a brief rendezvous in 1986 that transformed our understanding while simultaneously revealing how much we still don't know about this sideways world spinning at the edge of human exploration. Imagine being the only person ever to visit a distant relative's house, knowing that your brief afternoon there might be the only glimpse your family gets of that mysterious cousin's life for decades, or perhaps centuries to come. This was the profound responsibility carried by Voyager 2 as it approached Uranus in the winter of 1986, humanity's sole ambassador to the sideways world, bearing our eyes and curiosity across nearly 2 billion miles of cosmic emptiness. Picture the spacecraft itself, no larger than a small car, bristling with cameras and instruments that represented the absolute pinnacle of 1970s engineering. By the time it reached Uranus, Voyager 2 had already been travelling for 8.5 years through the cold vacuum of space, powered by the steady decay of plutonium in its radioisotope generators, and guided by navigation so precise that mission planners could predict its arrival time to within minutes across a journey spanning decades. The loneliness of that final approach cannot be overstated. By January 1986, radio signals from Earth took 2.5 hours to reach the spacecraft, and another 2.5 hours for any response to return. It was like trying to have a conversation with someone on the far side of a vast cathedral, where every exchange of words requires most of a working day to complete. Mission controllers at the Jet Propulsion Laboratory could only watch and wait as their mechanical explorer executed commands that had been uploaded hours earlier, trusting that the spacecraft's primitive computer, less powerful than a modern calculator, would carry out its cosmic choreography without human guidance. The encounter itself unfolded with the careful precision of a ballet performed in slow motion. On January 24, 1986, at exactly 5:59 p.m. Pacific Time, Voyager 2 swept past Uranus at its closest approach, 81,500 kilometers above the planet's cloud tops. To put this in perspective, that's closer than many satellites orbit Earth, yet it represented the culmination of humanity's longest journey to that point, a voyage that had carried our instruments farther from home than any human artifact had ever travelled. The timing was both fortunate and limiting. Voyager 2 arrived at Uranus during the planet's southern summer solstice, when the South Pole pointed almost directly at the Sun and the spacecraft's trajectory. This meant that Voyager could study the sunlit southern hemisphere in unprecedented detail, but the northern hemisphere remained largely shrouded in the darkness of Uranian winter. It was like being invited to explore a vast mansion, but being told you could only visit half the rooms, better than never seeing the house at all, yet tantalizing in its incompleteness. The images that began streaming back to Earth revealed a world that was both exactly what scientists expected and completely surprising. The featureless blue-green disk they had observed through telescopes was indeed featureless, showing almost no atmospheric structure visible to Voyager's cameras. Unlike Jupiter's dramatic bands and Saturn's subtle zones, Uranus presented an almost perfectly uniform face to the approaching spacecraft, as smooth and enigmatic as a sphere of polished jade. Yet this apparent blandness masked profound discoveries that would reshape our understanding of ice giant planets. Voyager's magnetometer, designed to detect the invisible magnetic fields that surround worlds, found that Uranus possessed magnetism, but not in any configuration that planetary scientists had anticipated. The planet's magnetic field was tilted nearly 60 degrees from its rotational axis and didn't even pass through the planet's center, offset by about a third of Uranus's radius. Imagine trying to navigate with a compass on such a world. Magnetic north would point in a direction that bore no relationship to the planet's spin, creating navigational chaos that reflected deeper mysteries about how Uranus generates its magnetic field in the first place. The discovery suggested that the planet's interior structure was as disrupted and unusual as its sideways rotation, perhaps another legacy of whatever ancient catastrophe had knocked the world onto its side. The spacecraft's instruments also detected Uranus's faint heat signature, confirming what ground-based observations had suggested. This ice giant radiates almost no excess energy into space. Unlike Jupiter, Saturn, and Neptune, which all glow with internal warmth left over from their formation, Uranus appears to have lost its primordial heat source. The reasons for this thermal deficit remain mysterious even today, but Voyager's measurements provided the precise data needed to confirm that Uranus truly is the coldest of the giant planets. Perhaps the most visually striking discoveries came from Voyager's study of Uranus's moon system. The spacecraft's trajectory was carefully designed to provide close encounters with several of the major satellites, revealing worlds of startling diversity and complexity. Miranda, the smallest of the major moons, proved to be a geological wonderland, its surface a chaotic patchwork of different terrain types that looked like pieces of several different worlds, stitched together by some cosmic seamstress. The images of Miranda's fractured landscape sent shockwaves through the planetary science community. Here was a moon barely 500 kilometers across, displaying some of the most dramatic topography found anywhere in the solar system. Towering scarps rose kilometers above the surrounding plains, while parallel ridges and grooves created patterns that resembled nothing so much as the result of a world being taken apart and reassembled by forces beyond earthly experience. Standing on Miranda's surface would be like exploring an alien archaeological site, where the artifacts were entire landscapes. You might walk across ancient, heavily cratered terrain only to find yourself suddenly at the edge of a cliff, overlooking smooth plains marked by parallel ridges that extend to the horizon. The gravity would be so weak, only about 1% of Earth's, that a good jump could carry you dozens of meters through the airless space above the surface, giving you a bird's-eye view of geological chaos frozen in time. Voyager's cameras also provided the first detailed images of Uranus's other major moons, revealing that each one tells its own story of formation and evolution in the outer solar system. Titania showed the scars of ancient geological activity, vast canyons that speak of a time when the moon's interior was warm enough to drive tectonic processes. Ariel displayed smooth plains that suggested relatively recent resurfacing events, while Oberon and Umbriel showed the heavily cratered surfaces typical of worlds that have remained largely unchanged for billions of years. The discovery of additional small moons added to the complexity of the Uranian system. Voyager found 10 previously unknown satellites, most of them tiny, irregularly shaped worlds that orbit close to Uranus and help shepherd the planet's ring system. These small moons provided crucial insights into how ring systems maintain their structure over geological time. The gravitational influence of shepherding satellites keeps ring particles confined to narrow bands, rather than spreading out into diffuse, unstructured clouds of debris. The ring system itself revealed new layers of complexity under Voyager's scrutiny. The narrow, dark rings discovered from Earth in 1977 proved to be part of a more elaborate system of at least 11 distinct components, each with its own orbital characteristics and particle properties. Some rings were perfectly circular, others slightly elliptical. Some maintained constant width throughout their orbits, while others varied dramatically in thickness from one region to another. The particles that make up these rings turn out to be darker than charcoal, reflecting only about 2% of the sunlight that strikes them. This extreme darkness suggested that the rings are composed of organic compounds, complex carbon-based molecules that have been processed by radiation and cosmic impacts over millions of years. Its material so dark that if you could scoop up a handful of ring particles, they would look like chunks of cosmic charcoal, blacker than almost anything found on Earth. The cultural context surrounding Voyager's encounter with Uranus adds another layer of meaning to this cosmic achievement. January 1986 was a complex time for space exploration, just 4 days after Voyager's closest approach to Uranus. The Space Shuttle Challenger exploded during launch, killing all 7 crew members and casting a shadow over America's space program. The triumph of robotic exploration at Uranus became intertwined with tragedy closer to home, creating a bittersweet moment in the history of space exploration. Yet Voyager 2's success at Uranus also demonstrated the remarkable achievements possible through international cooperation and long-term scientific planning. The spacecraft carried instruments contributed by scientists and engineers from multiple countries, and the data it collected was shared freely with the global scientific community. In an era of political tension and international conflicts, Voyager represented humanity at its best, curious, collaborative, and committed to pushing the boundaries of knowledge for the benefit of all. The technical challenges overcome during the Uranus encounter pushed the limits of 1980s technology. At Uranus's vast distance from the Sun, sunlight is nearly 400 times fainter than it is at Earth. This meant that Voyager's cameras required much longer exposure times to capture usable images, which in turn meant that the spacecraft had to rotate slowly during imaging to keep its cameras pointed at their targets while compensating for its own orbital motion. Picture the delicate precision required for this cosmic photography. Voyager had to spin at exactly the right rate to keep celestial objects motionless in its camera frames while travelling at tens of thousands of kilometers per hour through space. The slightest error in pointing or rotation rate would blur the images beyond recognition. Yet the spacecraft executed this complex dance flawlessly, returning hundreds of sharp, detailed photographs that remain our best views of the Uranian system nearly 4 decades later. The data transmission itself represented another technological marvel. By the time Voyager reached Uranus, its radio transmitter, no more powerful than a refrigerator light bulb, had to send signals across nearly 3 billion kilometers of space. The radio telescopes of the Deep Space Network, coordinated across sites in California, Spain and Australia, had to work together to collect these faint whispers from the edge of the solar system. Each image and measurement took hours to transmit back to Earth, arriving as streams of digital data that were painstakingly assembled into the photographs and scientific observations that revealed Uranus's secrets. The entire encounter generated only a few days' worth of close-up observations, yet the analysis of that data continues even today, as new techniques and computational methods reveal details that couldn't be extracted from the raw information when it first arrived. The melancholy of Voyager's brief visit to Uranus lies partly in its singular nature, Unlike Mars, which has been visited by dozens of spacecraft, or Jupiter and Saturn, which have been studied by multiple missions, Uranus has been the destination for only this single visitor. All of our detailed knowledge about the planet's atmosphere, magnetic field, rings and moons comes from those few precious hours when Voyager 2 swept through the Uranian system like a cosmic tourist on an impossibly brief layover. The encounter also highlighted the challenges inherent in exploring the outer solar system. The journey to Uranus takes the better part of a decade, even when using gravitational assists from other planets, and the communication delays make real-time control impossible. Future missions to Uranus will require the same kind of long-term commitment and international cooperation that made Voyager possible, along with advances in technology that can operate autonomously in the cold darkness for years or decades. As Voyager 2 departed Uranus and continued on its trajectory toward Neptune, it carried with it the satisfaction of a job well done and the poignancy of a farewell that might last for generations. The spacecraft had fulfilled its role as humanity's ambassador to the sideways world, revealing mysteries and raising new questions in equal measure. The images and data it collected transformed Uranus from a featureless disk in telescopes into a complex, dynamic world with its own unique personality and history. Tonight, nearly 4 decades after that encounter, Uranus continues its slow roll through the outer darkness, its rings spinning silently around its tilted equator, its moons following their literary orbits through space. The planet remains largely unchanged from how Voyager found it, yet our understanding continues to evolve as we develop new ways to interpret the data collected during those brief, precious hours of close observation. Yet even as we celebrate Voyager's remarkable achievements at Uranus, we're reminded that every answer leads to new questions. Every discovery opens doors to deeper mysteries. The sideways world continues to challenge our understanding of planetary formation and evolution, presenting puzzles that may require future generations of spacecraft and scientists to solve. Mysteries that whisper of secrets still waiting to be discovered in the patient darkness of the outer solar system. Picture walking through a vast library at twilight, where most of the books remain unopened and entire wings stretch into shadow beyond the reach of lamplight. The few volumes you've managed to read, scattered pages glimpsed by candle flame, hint at epic stories and profound secrets. Yet whole shelves of mysteries remain locked away in darkness, waiting for someone brave enough to venture deeper into the unknown. This is where we find ourselves with Uranus, holding a handful of pages from Voyager's brief visit, while an entire cosmic library of secrets spins silently in the outer darkness, patient as starlight. Nearly 4 decades have drifted past since human eyes last gazed upon that pale blue-green disk through Voyager's cameras, and in that time, Uranus has barely completed half a revolution around the distant sun. The world that our solitary visitor encountered during its endless southern summer is now slowly, glacially, turning its face toward equinox, a transition so gradual that seasons change more slowly than civilizations rise and fall on Earth. Imagine what might be stirring in that alien atmosphere as regions that have slumbered in decades-long winter begin to taste their first whispers of sunlight in a human generation. Does the air itself remember how to move after such stillness? Do clouds form like morning mist over a landscape waking from the deepest sleep? We can only dream of the atmospheric poetry that might be unfolding across those distant skies, written in a language of methane and hydrogen that no human eye has learned to read. The seasonal mystery of Uranus reads like a story told in geological time, each chapter lasting longer than the span between ancient Rome and the modern world. Picture standing on that tilted world during the slow transition from winter to spring. Not the familiar changing of earthly seasons measured in months, but something vast and patient, unfolding across decades like the growth of mountains or the erosion of canyons. Imagine what it might feel like to witness such a season change, if you could somehow survive on Uranus's cloud tops. For years, you might watch the same stars wheel overhead in unchanging patterns, while a pale sun traces its slow circles through the alien sky. Then, almost imperceptibly, the light begins to shift. The sun's path tilts slightly higher with each passing year, casting new shadows across cloud formations that have remained static for decades. The very air around you might begin to stir as temperature differences finally become large enough to drive atmospheric circulation. This is weather, as geology, meteorology operating on timescales that dwarf human civilizations. A single storm on Uranus might persist longer than the Roman Empire, growing and evolving through patterns too slow for any individual observer to comprehend. The clouds that form during one season might be inherited by the next, like family heirlooms, passing through atmospheric dynasties that span centuries. From our distant Earth, astronomers catch occasional glimpses of this cosmic awakening, subtle brightenings that appear and fade in Uranus's atmosphere, like distant lightning flickering behind clouds. Sometimes a pale spot emerges from the planet's characteristic uniformity, persists for months like a slow blooming flower, then gradually fades back into the atmospheric silence. These fleeting features tantalize us with hints of weather patterns so alien and extended that they challenge our very understanding of what it means for a planet to have seasons. Deep beneath Uranus's bland surface lies another kind of mystery entirely, an interior architecture built from materials that exist nowhere in our earthly experience. Imagine descending through layers of increasingly exotic matter, where familiar substances like water and ammonia are transformed by crushing pressures into phases of matter that border on the alchemical. Scientists speak of superionic ice, crystal lattices, where oxygen atoms remain fixed, while hydrogen flows like liquid metal between them, creating materials that are simultaneously solid and liquid, ice and conductor. The journey inward through Uranus would be like descending through the layers of an alien ocean, where the water itself changes its fundamental nature with depth. First, you would pass through the relatively familiar realm of hydrogen and helium gas, thin and cold but still recognizable from earthly experience. Deeper, the pressure would begin to compress these gases into states that blur the line between liquid and gas, creating fluid mediums that exist nowhere on our planet's surface. Further still, you would encounter the realm of the ices, not the simple frozen water of earthly winters, but exotic compounds where methane, ammonia, and water exist, under pressures so extreme that their molecular structures become fluid sculptures, constantly reshaping themselves according to forces that would crush any earthly material. Here, temperature and pressure create a chemistry of transformation, where elements behave according to rules written in the deep physics of matter, under extreme conditions. The very heart of Uranus might contain a core of rock and metal more massive than our entire Earth, yet buried so deeply beneath layers of compressed ices that it might as well exist in another dimension. This core would be a world within a world, perhaps iron and nickel and silicate minerals, compressed into crystalline structures that exist nowhere in our solar system's inner regions. The boundary between core and mantle could be a realm where familiar chemistry breaks down entirely, where the basic rules governing matter transform into something that would seem like magic to anyone who has known only the gentle pressures of Earth's surface. Future explorers of this hidden realm would need instruments that can listen to the planet's deepest whispers, seismometers, sensitive enough to detect vibrations travelling through materials that have never been reproduced in earthly laboratories. These cosmic stethoscopes could reveal the internal architecture of Uranus, the way ultrasounds map a human heart, showing us chambers and structures built from ice and pressure and time beyond all earthly measure. The magnetic field that surrounds Uranus presents perhaps the most beautiful puzzle of all, an invisible geography written in forces that point in impossible directions. Picture trying to navigate a world where every compass needle points toward a magnetic north that bears no relationship to the planet's spinning, where magnetic field lines tangle and twist through space in patterns that seem to mock our understanding of how planets should generate their magnetism. This isn't simply a matter of academic curiosity. Magnetic fields are the shields that protect atmospheres from the solar wind's constant erosion, the invisible armour that determines whether a world can hold on to its air across geological time. Understanding why Uranus's magnetic field behaves so strangely could unlock secrets about planetary formation, atmospheric evolution, and the very processes that make worlds habitable or hostile to life. The moons of Uranus float through space like frozen poems, each one carrying stories we've barely begun to decipher. Miranda's chaos landscape might hide beneath its fractured surface the chemical signatures of ancient warm periods when liquid water flowed through caverns carved in ice. These hidden seas would have been dark as midnight oceans, but they might have lasted long enough for complex chemistry to unfold, reactions that could have created the building blocks of life, or perhaps even life itself in forms so alien we wouldn't recognize them. Picture drilling through the icy crust of these distant worlds, following boreholes that spiral down through layers of frozen history toward hidden seas that might still slumber in the darkness. Each kilometre of descent would reveal new chapters in the geological autobiography of these moons, layers of impact debris mixed with episodes of internal melting, creating stratigraphic records that could be read like tree rings to understand the violence and quiet periods that have shaped these worlds across billions of years. The water found in such hidden oceans would be older than complex life on Earth, seasoned with minerals leached from rocky cores and stirred by tidal forces that operate across timescales measured in millions of years. Such seas would be natural laboratories where organic chemistry might have experimented with molecular combinations impossible in Earth's warm, oxygen-rich environment. The darkness would be absolute. No sunlight has ever penetrated these depths, but the chemistry of life often thrives in such conditions, finding energy in chemical gradients rather than photosynthesis. Titania and Oberon, with their ancient surfaces scarred by impact craters and tectonic fractures, might harbour different kinds of secrets. Their interiors could contain vast chambers where liquid water once flowed through networks of caves and underground rivers, creating environments that persisted for millions of years before finally freezing solid. These frozen caverns would preserve whatever chemical processes occurred during their liquid phases like geological time capsules, waiting for future explorers to unlock their secrets. Even the smallest moons in the Uranian system might hold surprises. These irregularly shaped worlds, most likely captured asteroids or comets, could be time machines carrying materials from the outer reaches of the solar system, or even for interstellar space. Their compositions might include organic compounds and water ice that formed in the cold molecular clouds between stars, providing samples of the raw materials from which planetary systems are built. The technology required to explore these mysteries reads like a wish list for cosmic magicians. Future spacecraft would need to operate autonomously for decades in conditions so harsh they would instantly destroy any unprotected earthly machine. They would need artificial intelligence sophisticated enough to make split-second navigation decisions when radio signals from Earth take hours to cross the void, power sources that can function in sunlight so weak it barely qualifies as illumination. Landing on the moons of Uranus would require precision navigation that makes Apollo's lunar landings seem simple by comparison. Picture spacecraft the size of small buildings settling onto surfaces where gravity is so weak that a careless step could launch you on arcs that take minutes to complete, where the horizon curves away so sharply that you might lose sight of your landing craft by walking a few kilometers in any direction. Yet perhaps the most profound mystery surrounding Uranus lies not in its exotic interior or alien moons, but in what its very existence tells us about planetary systems throughout the galaxy. As we discover thousands of worlds orbiting other stars, we find that Neptune-sized planets are among the most common cosmic architectures. Ice giants like Uranus appear to be the universe's preferred method for building mid-sized worlds in the cold outer reaches of stellar systems. This suggests that somewhere among the billions of stars visible on clear nights, countless ice giants roll through their own versions of sideways orbits, experiencing seasons that last decades and generating magnetic fields that point in impossible directions. Some of these distant cousins of Uranus might harbour moons with subsurface oceans, where alien biochemistry explores possibilities that terrestrial life has never imagined. The question of whether we will ever return to Uranus carries its own kind of melancholy beauty. The orbital mechanics that govern journeys to the outer solar system operate on timescales that challenge human patience and political will. Launch windows that provide efficient trajectories to Uranus open only every few years, and the journey itself requires the better part of a decade, even when using gravitational assists from other planets. Future generations might develop technologies that make such voyages routine, perhaps fusion rockets that can cut the travel time to mere years, or space-based construction facilities that can build exploring spacecraft too large to launch from Earth's surface. But for now, Uranus remains tantalizingly beyond our reach, a world we can study only from a distance measured in billions of kilometers and decades of travel time. There's something profoundly romantic about mysteries that unfold across such vast scales of time and distance. Uranus reminds us that the universe still operates according to rhythms far grander than human experience, that there are stories being written in the cosmic darkness that we may never fully read. Its secrets are patient ones, content to wait for centuries or millennia until curious minds develop the tools and techniques necessary to unlock them. The sideways world continues its ancient role through space, carrying with it questions that touch the fundamental processes of planetary formation and evolution. Every day that passes adds another page to its seasonal story, another layer to the atmospheric changes that might be occurring in its alien skies. Its moons trace their literary orbits through the darkness, perhaps harbouring oceans that have remained hidden since the solar system's youth. In contemplating these unresolved mysteries, we find ourselves in the position of astronomers throughout history, standing at the boundary between the known and unknown, armed with instruments and theories that can peer only so far into the cosmic darkness before encountering phenomena that stretch our understanding beyond its current limits. Uranus stands as a monument to the vast amount we still don't know about our own solar system, a reminder that even in our cosmic neighborhood, worlds exist that challenge every assumption we make about how planets should behave. Tonight, as that distant ice giant continues its patient journey around the Sun, it carries with it all the secrets we've yet to discover. Atmospheric dramas unfolding in alien skies, geological processes operating in the darkness of hidden interiors, and perhaps even the chemistry of life in subsurface seas that have never known starlight. These mysteries wait in the cosmic darkness like unread books in that twilight library, their stories ready to unfold for anyone brave enough to make the long journey into the unknown. Yet even as we contemplate the vast mysteries that Uranus still conceals, there's something deeply satisfying about the journey we've already taken together. From Herschel's accidental discovery to Voyager's lonely encounter, from the sideways world's impossible seasons to its dark rings spinning in orientations that challenge cosmic common sense, a reminder that the universe still holds wonders capable of overturning everything we thought we knew about the architecture of worlds. As our gentle journey through the realm of the sideways world draws to a close, imagine looking back across the cosmic distance we've travelled together, from William Herschel's garden in Bath to the frozen plains of Miranda, from the accidental discovery of dark rings to the patient mysteries that still await future generations of explorers. We began with a musician peering through his handmade telescope on a March night in 1781, and we conclude with a world that continues to roll through the outer darkness, carrying secrets that may take centuries to fully understand. There's something profoundly moving about Uranus's role as the boundary guardian between the familiar and the truly remote. It stands at the threshold where the classical planets give way to the modern discoveries, where naked eye astronomy yields to the age of instrumental exploration. Beyond Uranus lies only Neptune, and then the vast emptiness that stretches toward the stars, a reminder that our solar system has edges, places where the Sun's family of worlds fades into the cosmic deep. The sideways world has taught us that the universe doesn't arrange itself for our convenience or comfort. It operates according to its own mysterious logic, shaped by catastrophes so ancient we can only guess at their nature and processes, so patient they unfold across timescales that dwarf human civilizations. In Uranus's impossible orientation and decades-long seasons, we find a humbling reminder that cosmic forces operate on scales far grander than our earthly experience. Picture Uranus as it exists tonight, a pale blue-green disk spinning on its side in the cold darkness, its rings tracing impossible circles through space, while moons named for Shakespearean characters dance their literary orbits around their tilted parent. The same methane molecules that give the planet its ethereal colour are catching starlight and solar photons in the same patient dance they've performed for billions of years, indifferent to human observation, yet somehow essential to the quiet beauty that makes this world unique among all the planets we've discovered. The featureless atmosphere that once frustrated astronomers now seems less like a limitation than a different kind of perfection, the aesthetic of subtlety rather than drama, of whispered secrets rather than bold proclamations. Uranus reminds us that not every cosmic beauty needs to announce itself with Jupiter's storms or Saturn's brilliant rings. Sometimes the most profound mysteries hide behind masks of uniformity, waiting for patient observers willing to look beyond surface appearances. From Herschel's accidental discovery to Voyager's lonely encounter, the exploration of Uranus has been a testament to human curiosity and ingenuity. Each revelation, the planet's extreme tilt, its dark rings, its diverse family of moons, has expanded our understanding not just of this single world, but of the fundamental processes that shape planetary systems throughout the universe. The sideways world has been our teacher, showing us that planets can exist in configurations we never imagined and behave according to rules we're still learning to understand. The literary names carried by Uranus's moons add a layer of poetry to this distant system that speaks to something essential about human nature. We are storytelling creatures, beings who find meaning through narrative and connection. When we look at Miranda's fractured landscape, we can't help but think of Shakespeare's innocent daughter, marvelling at her brave new world. When we contemplate Titania's stately orbit around her sideways planet, we imagine the fairy queen ruling over a domain far stranger than any earthly forest. This connection between science and art, between cosmic discovery and human creativity, represents one of the most beautiful aspects of our relationship with the universe. We don't just study distant worlds, we adopt them into our cultural imagination, making them part of the ongoing human story. Uranus, with its Shakespearean moons and impossible orientation, has become not just an object of scientific interest, but a character in the grand narrative of cosmic exploration. The ice giant classification that now includes Uranus alongside Neptune has revolutionized our understanding of planetary formation and evolution. These worlds built from ice and rock, rather than hydrogen and helium, represent a different experiment in planetary architecture, one that appears to be remarkably common throughout the galaxy. As we discover thousands of exoplanets orbiting other stars, we find that Neptune-sized worlds are among the universe's most popular planetary designs. This suggests that somewhere in the darkness between stars, countless cousins of Uranus roll through their own sideways orbits, experiencing seasons that last decades and generating magnetic fields that point in impossible directions. Some of these distant ice giants might harbour moons with subsurface oceans, where alien chemistry explores possibilities that terrestrial biochemistry has never imagined. In studying our own sideways world, we develop tools for understanding planetary systems throughout the cosmos. The technology required to return to Uranus speaks to humanity's growing capabilities as a spacefaring species. Future missions will require innovations that push the boundaries of autonomous spacecraft operation, power generation in the outer solar system, and communication across billions of kilometers of empty space. These challenges are not merely technical hurdles, but opportunities to develop technologies that will enable exploration of even more distant and exotic destinations. Yet perhaps the most important lesson that Uranus teaches is patience. This is a world that reveals its secrets slowly, across timescales that challenge human attention spans and political cycles. Understanding Uranus requires the kind of long-term commitment that spans generations, connecting past discoverers with future explorers through chains of curiosity and wonder that transcend individual lifetimes. The seasonal changes that unfold across Uranus's 84-year orbit operate on timescales that dwarf human planning horizons. A complete study of how this world's atmosphere responds to its extreme seasonal cycles would require observations spanning multiple human generations. This forces us to think beyond immediate results and quick answers, to embrace the kind of patient science that builds understanding layer by layer across decades and centuries. There's something almost meditative about contemplating Uranus's patient journey through space. While we rush through our daily lives measured in hours and minutes, the sideways world maintains its stately progress according to orbital rhythms that have remained unchanged for billions of years. Its rings continue their ancient dance around the planet's tilted equator. Its moons trace their literary paths through space, and its atmosphere maintains its enigmatic uniformity despite whatever dramas might be unfolding in its hidden depths. The mysteries that Uranus still conceals, from the source of its magnetic field to the chemistry of its moon's possible subsurface oceans, remind us that our solar system remains largely unexplored. Even in our own cosmic neighborhood, worlds exist that challenge every assumption we make about planetary behavior. The sideways world stands as a monument to the vast amount we still don't know about the processes that create and shape planets. As we drift toward the end of our journey together, carried by the same kind of patient momentum that moves Uranus through its distant orbit, we can appreciate how this remarkable world has enriched our understanding of cosmic architecture. From a single point of light noticed by a musician astronomer to a complex system of rings, moons, and atmospheric mysteries, Uranus has grown in our understanding, while remaining essentially itself, sideways, subtle, and surprisingly profound. Tonight, as you settle into whatever comfortable position you've chosen for this cosmic journey, remember that somewhere in the darkness above, the tilted guardian continues its ancient watch at the edge of our planetary neighborhood. Its pale blue-green light travels across billions of kilometers to reach our telescopes, carrying with it the patient message that the universe still holds wonders beyond our current understanding. In its sideways spin and impossible seasons, in its dark rings and literary moons, in its featureless atmosphere and tilted magnetic field, Uranus embodies the ongoing mystery of cosmic existence. It reminds us that the universe is far more creative and surprising than our theories suggest, capable of building worlds that challenge every assumption about how planets should form and behave. The sideways world waits in the cosmic deep, patient as starlight, beautiful in its alien perfection, ready to share more of its secrets with anyone curious enough to look closely and patient enough to listen to stories told across geological time. In its distant orbit, Uranus carries forward the memory of ancient catastrophes and the promise of future discoveries, a tilted guardian watching over the boundary between the known and the unknowable, forever spinning its way through the patient darkness of the outer solar system. Sleep well, fellow travelers of the cosmic deep. In your dreams tonight, may you find yourself drifting among worlds of impossible orientation, where seasons last lifetimes and moons bear the names of poets' dreams, where the patient mystery of existence continues its ancient dance in the gentle darkness between stars.